Okay. So now we're going to talk about chapter 1.2. We're done with the moral talk about AI, so we can just remove that. So with the statement, um, for every 1 second in English, if you're given this task, how would I possibly represent this in math? Oh my God, my computer's always slow when this happens. Okay, update on my computer, on my tablet, please. And it's not showing up on my tablet. Oh, awesome. Well, I'm gonna assume, oh, there it is. Okay. All right, for everyone. Um, okay, that's good. Okay. Let me just erase all this then. For every 1 second, I get one cat per 1 second. Oh, for 10 seconds. For 10 seconds. Um, delete this part. I'm not gonna wait for that again. So I'm gonna make it a little bit smoother over here. And I'm gonna make it a little bit smoother over here too. Now, with that said, how would you graph this? I would graph this by saying 10 like this over here. Now, this would be the time, and this would be the y domain of cat. And basically, you can see from here that every once t is contained by 0 and 10, as you can see, because it's contained over here. And you get 10 cats in 10 seconds, I guess. Uh, the that is how it works, and now that's the mathematical representation that you can get. Now, I wrote R over here. It contains to infinity, negative infinity to infinity. Um, that's just all real numbers representing. You don't need it for this. I just wanted to show that off there. That's basically it. Um, all right, we're done with that one. That was fast. Now we're going to do, oh, the loan one. The loan one says, my loan cost me $2 every year for 50 years. I had $50 in this basic, okay, this fake play. Okay. So basically you have 50 bucks and every for every year. How the fuck do you lose $100? 50 years. Yes, yes, um because 2 times 50 is 100, so you lose $100. Uh, and then the rate of soap. And then next here, maybe I should have done this first because it makes more sense. But um, what I did over here was describe the rate of change of over here, which is dx and dy, because that's the fundamentals of calculus basically later on. Dy equal delta y, and then dx equal delta x. It doesn't matter for this one because it's linear. It's both the same thing. And then you figure out that you can scale those two up to different things to get different versions of you know, what's the word? Different different figurines. You'll see that later. Now you get Cartesian coordinate system. Basic things. You can use Khan Academy to learn this. It's not hard. Um, okay, maybe I need to do the. I I probably should have done the proof for this. I didn't think I needed to, but I should have done the proof. What I'm talking about is y equal mx plus b versus y minus y1 equal mx minus x1. This and this the same thing. There's a proof for it. I don't remember it on top of my head, but I probably can derive it very easily. Basically, b is basically y equal mx parentheses minus mx1 plus y, which makes y equal mx minus mx1 plus y1. So it's y1. So you can see b equal negative x1 plus y1. Pretty cool, right? Yeah. Uh, yeah. It's not that important, actually. Thinking about it, there was a reason I didn't really talk about it. It wasn't really necessary for anyone to know, so I don't know why I brought it up. Anyway, next you understand how to do this. So when you have y equal 3x plus 6, you plug in a bunch of digits, but let's just plug in x equals 0, and then that gives you y equals 6 when you plug 0 in here. And then you do x equal negative 1, which gives you y equal should be 3. I get these two. Now, this 2 points is enough to define any linear line like this. Because you have this one and then you have this one. And then so 2 points defines a linear line. Always remember that. For some reason put inflation here. I'm thinking of deleting it. There's no reason for me to put inflation. Um, Clocks, and why am I talking about polygons here? I made this a long time ago, and I guess I was desperate for space. Okay. Now, I do it a few more times. You can do it on your own if you want. And then I finally do these four because these showcase what this is. So when you have a general function, and then this is beyond just linear functions, but for now we're talking about linear. So if you have a number like this, the number allows it to shift down. If a number like this, it shifts up. Now if you have a number like this, it shifts to the right. If you have a number like this, it shifts to the left. What does that even mean? Well, it showcases how it shifts, basically. If you have something complicated like y equal parentheses x plus number parentheses negative 4, you can figure out, this over here shifts everything to the left, that many spaces, and then you go up -4. Where does this even play out often is if you go to higher order terms, or even if you go to polar coordinates, if you go into y equal x square. Well, if you do y equal, we do this later on, but if you do 1, you just shift everything up. If you do y equal x minus 1 squared plus 1, you shift everything to the right by 1. If you do it in polar coordinates, if you do polar, if you do r to some function over here, and you do plus a, you actually do a radial push. You'll see this is a r function, radial push, and it's pretty cool. I got some interesting airfoils by that method by molding molding uh, lips into a shape. You can do it. Now there's a Kalskaya method, but I did it a different way and it worked out well. I didn't I don't think it's ever applicable, so I never really talk about it other than on this textbook. Um anyway, we're done. Let me stop sharing, right? Because we're done. Yeah. If you want to know about that way, because I don't think I ever wrote it down, but I did wrote it down somewhere. No, I did it in my textbook somewhere.